Let us recall the definition of pathwise connected. A topological space X is pathwise connected if and only if for x comma y is in capital X, for x y in X there exists a continuous function, there exists a continuous function say f depends upon xy from closed interval 0 1 to the topological space X such that at 0, that is at initial point it is X, f at 1 that end point is Y. Then we say that the topological space X is pathwise connected. In fact, it is, we know that if you have any closed interval a comma b, let us say that A, assume that A is less than B in R, A comma B belongs to R, and we have the closed interval 0 comma 1. So then we have the natural way we can define a homeomorphism between closed interval 0 1 and closed interval a comma b, that is define a map say G from closed interval 0 1 to closed interval a comma b such that G at t is 1 minus t times A plus t times B for all t belongs to closed interval 0 1. Then when t is 0, what is G at 0 is, we will get A, G at 1 will G at 1 will get B. So this is a continuous function. Also it is easy to prove that this function G continuous, not only G continuous, G is bijective, G is 1 1 and on 2, and G inverse from closed interval a b to 0 1 is to closed interval 0 1 is also continuous. So that is the function G is a homeomorphism. So using this, in fact you start with any, consider the function G inverse here f, where G inverse at A under G 0 goes to A. So under G inverse, G is continuous, G inverse is continuous, f is continuous, and this function is such that at A this is f of g inverse of A, which is same as f of 0 if we assume that f is a continuous function from closed interval 0 1 to x having the property that f at 0 is x, f at 1 is y, then this function, that is h equal to f composition g inverse, which is a continuous function such that h at A is f at 0 is x, that is h at A is x, and h at B is h of g inverse of B, which is same as h of 1, correct, f of, so we write h is equal to, yeah, that is h at B, h equal to f composition g inverse at B, but f of g inverse of B is 1. So, this is f at 1 is we have y. So, f at 1 equal to y, hence we, if there is a continuous function from closed interval 0 1 to x, then there is also a continuous function h from, we have h is a continuous function from closed interval a b to the topological space x, satisfying the condition that h at A is initial point x, h at B is the end point y. So, hence this closed interval can be replaced by any closed interval a comma b. So, and it has nice properties, like you consider the whole plane R2. Now, it is easy to see that this is pathwise connected. In fact, geometrically we see any xy. So, if you have x in the plane R2, that means x equal to some order pair x1 comma x2, and y is another element, say order pair y1 comma y2, then there is a straight line joining x and y. In fact, we define closed interval xy equal to set of all 1 minus t times x plus t times y such that t varies from 0 to 1, 0 less than or equal to t, less than or equal to 1. Then this is what we call it. I mean, in fact, we can see that this takes all the value between x and y for a given t. So, this will be 1 minus tx plus ty. At t is 0, you are at x, t at 1 y. This one can prove that this line segment is nothing but this set, which we call it closed interval x comma y. So, if you are given capital in R2, we have say xy in R2, fix x comma y in R2, xy is fixed, define f from closed interval 0 1 to R2 as the same map f of t equal to the line segment. It is a point in the line segment joining x and y, that is 1 minus t times x plus t times y. So, here what we mean is R2 with the usual topology. So, topology induced by the Euclidean metric. So, then this function f is continuous, then f is continuous and f at 0 is x, f at 1 is y. Hence, R2 is pathwise connected. In fact, we will have a nice lemma, in fact, like how to join two pieces. So, we have a curve say from x to y, again a curve joining y to z, say in the plane. Then in natural way we have a, what is curve mean? It is a continuous function from closed interval some, I mean that is what we have seen, either we can assume that the function is continuous from closed interval 0 1 to the plane such that f at 0 is x, f at 1 is y. Then this pair for will determine for a given element here, correspondingly we will have for any t comma f of t, it will be on the curve. I mean this continuous function will determine a curve. So, we will have a curve which will describe x to y. So, then we will have another curve, I mean another continuous function which will describe y to z. Now, we will see how to get a continuous, I mean how to join these two curves. So, for that what we need is a lemma called pasting lemma. Exactly at this point we are joining the two curves. So, we will just state the lemma, which is, I mean the proof of this lemma is, it is quite straightforward. So, we have a topological space x, topological space, y another topological space, capital A comma capital B, non-empty closed subsets of capital X. Now, define, we have function, we have a function f from capital A to y, the domain is A, that means you are considering A as a subspace of X, already A is closed in X. So, this is continuous, f is continuous, G from capital B to y also continuous, see the domain, here the domain for f is A, domain for G is B. So, in general they can be any sets. So, the A intersection B may be empty or it may be non-empty. Suppose if they are non-empty, that is there is a common point. So, that case what we need is at those common point F and G should coincide, that is further suppose that Fx equal to Gx for all x belongs to the A intersection capital B. In fact, we can write that x belongs to A intersection B, so it implies this. So, when intersection is empty, this condition is redundant, so it is not necessary. Then we can define a function, say h. Now you are joining the domain A union B to Y, define this as h of x equal to f at x. This is when x is in the domain A, when x is in A, and Gx when x belongs to capital B. So, note that when x is in the A intersection B, Fx equal to Gx. So, hence this is a well defined function. Then we can prove that, then define a function h is this way, then this function f is h is, then h from A union B to Y defined as above is continuous. This is also a continuous function. In fact, we have suppose we have two continuous function, say f at t, we have an arc like here in R2, we have a curve joining x and y. That means what? We have f, there will exist. So, we have fixed x y say in R2, then another point z. So, we have suppose our space here it is pathwise connected, we will get a continuous function f from closed interval 0 1 to that space say here R2 such that f at t is such that at the initial point it is x, f at 1 equal to y, and also there exists another continuous function say g from closed interval 0 1 to R2 such that g at 0 is now here, now we are given y and z. So, the starting point is y, end point is z. So, g at 0 is y and g at 1 is z. Now, we will use pasting lemma to give you a continuous function from x to z. in short, it is like telling that you are travelling from x to y, say let us say in 1 hour, and y to z another 1 hour. Now we want to have a function from x to, I mean the domain should be same closed interval 0 1. So essentially now we will like telling that you increase travel, go reach x to y in half of the time and remaining half of the time to reach y to z. So we will divide the domain into two parts, that is we will have our set A closed interval 0 to half, capital B equal to half to 1. Now define a function h from closed interval 0 1 to R2 as h at now t, see when t at 0 we are going to be at x, but t at half we are going to be at y. So this should be equal to f at 2 times t, because when t equal to half 2 times t will become 1, f at 1 is y. So this is when 0 less than or equal to t less than or equal to half. So we have divided the domain here, the 0 to 1, here we are 0 to half, that is our set A, and common point is half. So and define this as g at 2t, because now when t equal to half, so you should be at that correspondingly when t 2t minus 1. So now when t equal to half, this g will be g at 0, g at 0 is y. So g at 0 will be y, and similarly that is h at half is y, h at 1, that is here it is 1, t is 1, g at 1, that is z. So then in fact what is first function is t goes to the composition f of 2t, t goes to 2t is continuous and f composition this function. So if we call it, this is f1 of t equal to 2 times t, then this is nothing but f composition f1 of t, that is same as f1 of t is 2t. So we will have a, this is a continuous function, t goes to f of 2t is continuous and t goes to g of 2t minus 1 is continuous. Now here the domain is half less than or equal to t less than or equal to 1, and at the common point, here the common point only half, at common point here when t equal to half f at 1 y, here g at half is 0, so that is y, f, that means both will coincide. So hence by pasting lemma h is continuous and this continuous function is such that h at 0 is x, h at 1 is z. So we can join essentially these two curves. If there is a path from x to y and if there is a path from y to z, then we have a path from x to z. So, that is what I mean, we can in fact define a relation and then we can prove that that relation is an equivalence relations. Okay, now let us see quickly that the pathwise connected is, as we expect, naturally it is stronger than connected. I mean, we can prove that if a topological space is X is pathwise connected. Suppose a topological space X is pathwise connected, then that imply that topological space is connected. So, let us assume that is as a result if X is a, let X tau with a topology X tau be a pathwise connected topological space, then X is connected. That means every pathwise connected space is connected. So, in fact in general the converse is not true. For some special type of sets, if it is a capital G and open subset of Rn, then we can prove that in fact every open set is also pathwise connected. So, let us see, this is almost very simple. So, we will assume that suppose this X is has a separation. So, prove suppose that means what, there exists non-empty either open sets say A comma B such that one they are disjoint, A intersection B is empty. Second, union, if you take A union B, the whole space X, that is X has a separation. Then what will happen, this A X is now given A is non-empty. So, take imply there exists X in A. Similarly, the set capital B non-empty imply this B will have some point say Y. Now, X is in A, Y in B, they are all subset of our topological space X which is pathwise connected. So, now we have X is in X, Y is in X, X is pathwise connected. So, X is pathwise connected implies there will exist a continuous function from closed interval 0 1 to X. Now, xy belongs to capital X, X is pathwise connected implies there exists a continuous function say f from closed interval 0 1 to X such that f at 0 is x, f at 1 is y. But now what is our x? This f at 0 now, f at 0 equal to x imply this 0, I mean we have what is f inverse of A will be set of all t in the domain such that f of t will be equal to f of t belongs to A, set of all t such that f of t belongs to A. Now we know that x is in A, so f at 0 belongs to A. So 0 will be in f inverse of A, implies 0 belongs to f inverse of A. Reason is since x is in A. Same way f of 1 is in f of 1 is y, that imply 1 belongs to f inverse of B, that means, and f is continuous, so hence the inverse image f inverse of A is open in our domain, is an open subset of closed interval 0 1. Similarly, f inverse of B is open in our domain closed interval 0 1. Further, what is our f of this f inverse of capital X is same as f inverse of x is A union capital B, which is same as f inverse A union f inverse B and the pre-image of the codomain. So that will be equal to the domain closed interval 0 1. So we have here this set, because x is here, this contain 0 belongs to f inverse of A. So this set is non-empty, open, this also f inverse of B non-empty and also open. So closed interval 0 1 is union of these two open set, and further f inverse of A intersection f inverse of B is same as f inverse of A intersection B, which is again empty. So that means this imply closed interval 0 1 is not connected. So whereas this is an interval. So that gives a contradiction. Hence x should be pathwise connected. Sorry, x is pathwise connected and hence x should be connected. That is, if x is not connected, we get a contradiction. So this would imply x is connected. When we assume that x is pathwise connected, then we have proved that x is connected. So every pathway is connected, topological space is connected. Let us quickly see how to prove a open subset of the complex plane or R2. For a open set, there is no difference between connected and pathwise connected. So let us say, let capital G, I mean we have capital G, a non-empty open subset of R2, or we can identify that with the complex plane C. So, an open subset of the complex plane, then in fact then capital G is pathwise connected. In fact, what we are going to prove is this is more useful in the complex analysis. So, that is if it is a connected set, if we have, let us say, so we have this, consider this interior points of this domain. So, we have only the interior points. So, not on the, I mean this point mean they are all boundary, any neighborhood of that will have points from inside as well as, I mean from the set A and complement. So, we consider only the points inside. So, this is like our set capital G. Now, we want to prove this set is pathwise connected. See, first let us see geometrically what we mean by this. So, then take a point, say small a, which is a complex number or either a equal to some a1 plus I a2, or we can identify that as order pair a1 comma a2. So, this topology is topology induced by the metric, that is the usual. If we take distance between Z1, Z2 is modulus of Z1 minus Z2, correct. So, we take any point A in G and any point B in G for any x, either xy, or we are using say A and B points in G, then we should be able to define a function, continuous function f from closed interval a b to this space. Consider capital G as a subspace of the complex plane, such that either a, so we can define, sorry, here the notation is close 0 1 to G with f at 0 is the initial point A, f at 1 is the end point B, or essentially what it mean is from there is a curve joining A and B, the curve should be inside the domain. So, we cannot, for example, here in this diagram we cannot, this direct line, here there are points which are not in the domain. So, otherwise we would have defined the function as t goes to 1 minus t times A plus t times B. Then this is our continuous function, mean at A it is, at t is 0 it is A, t at 1 is B, but there are points, this when t varies over closed interval 0 1, this set, this will describe the line segment which is not in our domain. So, it will not be a function f if we define this way, it will not be a function from closed interval 0 1 to G. So, whereas what we will do here is we will not be able to construct directly a continuous function. In fact, we will prove that any two points in the domain can be joined by a polygonal path. So, what we mean by a polygonal path mean? So, we have already defined the starting point, we will find A is our starting point say Z0, then we will get a point Z1. So, that means A, then we have say this is Z1, there is no order relation, this just there is a line segment joining A and Z1, this is straight line which is inside the domain. Then again there is another line segment joining Z1 and Z2, then Z2 and Z3, let us say, like that we have say Z3 to Z4. So, now then Z4 to say some, say that is the last point Zn, then Zn to the point B. So, I mean I leave it in a natural way. What is the union of, see what is the polygonal path, say capital P equal to closed interval A comma Z1, that is a line segment joining A and Z1, union Z1 comma Z2, union the Zn comma B. All these intervals are subset of G. So, that means union also subset of G. Then we say that there is a polygonal path joining A and B, that is what essentially this is our polygonal path joining this A and B. So, now in fact we can prove that, and this will now use the pasting lemma. There is a continuous function from A to Z1, then Z1 to Z2, just now we have proved exactly same way. Say A to Z2 continuous function, there is a path, then Z2 to Z3 the common point is Z2. So, by induction we can prove that there is a continuous function from A to, I mean with initial point A and end point B. So, enough to prove this, in fact a stronger version.